Hi everyone, in this three-part tutorial series we're creating a starlit night sky like this. In the first episode we created a star data loader class which took in our real life data and presented it in a way we could use. In this episode we're going to focus on creating the game objects using that data. Let's get started. First up, we're going to create another script called starfield. We need to attach this to a game object. If you put it on its own, then when you move about in the scene, you could end up outside the star field, and that would be bad. We actually want to parent these to the camera, so the stars are always centered around the camera. So we'll create a new parent game object to the camera and call that camera holder. You can then add the starfield script onto this. Whilst I'm here, I'll just turn off the skybox on my scene view to make this look nicer. The other thing I need to do, which I forgot in the previous tutorial, is in the resources folder, we need to rename bsc5 to bsc5.bytes. That enables it to be correctly identified as a text asset. Jumping into the starfield script, the first thing we want to do is load our star data. First, we'll need a couple of global variables to keep track of our objects. We have stars, which will be the list of type starDataLoader.star, and star objects, which will be the game objects associated with the stars. In our start method, we grab a reference to the star data loader class, then load the star data, assigning the resultant list to our stars variable. Now, we want to actually create the stars, so we'll initialize the list of game objects so we can add to them as we go. Use forEach to loop over the stars, and for simplicity, to start with, we'll create the stars as spheres, so we can use the helpful CreatePrimitive method with the primitive type .sphere as the parameter. Set the parent to our camera holder by using transform as the script is attached on this camera holder. As we mentioned before, that will mean our star field travels with the camera. I'll use this opportunity to name the stars their corresponding catalogue number. We set the local position to the star's position, and remember that we created them on the unit sphere, so we want to create a new private variable starfield scale and set this to 400 and multiply the position by this. This puts them far away, but crucially close enough that it remains within the camera's clipping planes, so we'll be able to see them. For the size, the star.size variable is a value between 0 and 1, so we can use this to lerp between our min and max star size. For these, we'll create some serialized variables so you can set them in the inspector. I've added the range attribute to clamp them between 0 and 100, though you'll not want the stars so big. Lastly, we use getComponent to find a reference to the mesh renderer and pull off the material. Then we can set the material color to the star color, and we add the star game object to our star objects list so we can access it later if needed. So let's take a look at that back in Unity. Hitting play, we can see lots of spheres representing our stars. That's starting to look cool. As a sanity check, here you can see straight in front of us that these three big blue dots are Orion's belt. It looks like everything's working so far. Switching into scene mode, you can see we've got a wonderful sphere of stars around our camera. If you select the camera holder and drag that around, you can see all the stars are pinned to this, so we'll be able to move around the game and the stars will appear fixed in far off positions. Let's quickly dive back into the code and allow us to look around so we can observe this a bit better. So let's add a fixed update. This is just like update, except it happens on a regular clock. It's usually used to do physics-like things, but we'll hook into it to do our camera movement because I'm being lazy. What this means in practice is that I don't have to worry about speed and using time.delta time to scale it. We use input.getKey to detect when mouse 1 is pressed. That's the right mouse button. We're going to mimic the Unity scene view movement here, so we'll use camera.main.transform to get the transform of the camera. We want to rotate this based on the mouse movement, so we can use the rotate around function. We want to rotate around the camera's current position, so that's argument 1. Then for looking up and down, we use transform.right as our rotation axis. Just imagine a big movie camera with a stick going through it, that's how we're rotating it. Input.getAxis mouse Y tells it to use the vertical mouse movement. Then for left and right, it's the same process, but we use vector3.up for the rotation axis. We don't use camera.up because that would change as you tilt the camera up and down. We must negate the mouse X movement so it moves in the manner we expect from Unity. Jumping back into Unity and hitting play, we can now gaze at all the stars. This is so cool, but the stars look a bit like little spheres and not like awesome stars. Also, if you open up the stats panel here, you'll notice we're drawing a crazy amount of vertices and triangles, and the FPS is already beginning to drop. So let's fix that by jumping back into our star field script. While stars are technically spheres, we don't actually want a 3D shape to represent them. For the most part, they're small specks of light. So what we'll do is swap out our sphere for a quad. That only has 2 triangles. However, whilst a sphere looks the same as viewed from any direction, a quad does not. You may jump to thinking that you need a billboarding script or a shader to handle this, but it's actually much simpler. As we've tethered the star field to our camera holder, the location of the camera is always in the same position, the center. So after setting the position, we can use the lookat method, passing in the position of the camera holder. This assumes that the camera is at the origin of our holder, which is true, so we're all good. There's just one of those Unity quirks where this actually means our quads will be facing away from the camera, so we just rotate them by 180 degrees to sort that out. Now jumping back into Unity, you can see in the game view that we have lots of little squares. I think we'll all agree that square is not a good look on a star, so let's create a shader to give us what we want. First, we'll create a shaders directory. Then we'll add a shader with create shader unlit, and we'll call this star shader. So before we create the shader code, let's consider what effect we want. We could simply render a circle on the quad, but we don't want hard edges. We want a more gradual fade out. However, something linear is likely to make our stars look fuzzy. So what function do we want? This is where I turn to my favourite online grapher, Desmos, if that's how you say it. There's a link in the description below. We're going to treat our quad as going from +1 to -1, so 0, 0, the origin is in the center. We'll get the fade effect by using transparency, so we don't have to do special things for all the varying colors of stars. So if we had something linear, like 1 minus x, we'd get a fuzzy circle like this. What we want is a much sharper drop-off, so we have a solid spot of light which quickly fades out. So 1 over x is going to work much better. If we zoom out, we can see that it's got a sharp drop-off we're looking for. Let's just scale it back a bit by doing 0.2 over x. That's much better, in the 0 to 1 range now. We want it to be 0 at the end of the quad, which will be 1, so subtract 0.2 from the equation to bring it to the line. We'll add on the restriction to x here in curly brackets to make it look better. Now we just need to cap the y value at 1 when x is small, and we can do this with the min. And there you have it. That looks good. It'll look like this on the shader. So let's dive into the shader code. First thing we want to do is add 2 new properties. First is _color, which will enable us to set the color of the star. It's important we use this exact name. This is a Unity shortcut that will enable us to use material.color to set this. Second, we have _size, which is a float, and we'll use this to set the size of the star. Let's jump to the vertex and fragment shaders to implement our logic, then we'll come back to the settings afterwards. For the vertex shader, we want to modify the vertices based on the size. So define this locally, and then we can simply multiply the vertices by the size. This works because the quads are centered around the origin in model space, so multiplying just scales it up. For the fragment shader, again, we'll need access to _color in this pass, so declare that. We don't want the color to be taken from the texture, so just delete that. We can use the UV coordinates which are automatically mapped for us on the quad to map our function. However, UV goes from 0, 0 to 1, 1, and we created our function under the assumption we were going from -1 to +1. So we can simply multiply the UV by 2 and subtract 1, which gives us what we want. Then, when we take the length of the transformed UV vector, this will give us the distance from the center. This is exactly what we need to put into our function. So our inverse distance, which was x in the Desmos plot, is going to be 0.2 divided by distance from center minus 0.2. Then in Desmos we had a min, but in fact HLSL has a nice helper function called saturate, which clamps our value between 0 and 1, which is exactly what we want. We can then set our color to be the material color, with the output of our function being the alpha parameter, which will fade it out. So we just need to make a few changes to the sub-shader so this works. As we're using transparency, we need to set the blend mode. I think if we have 2 stars close together, then we need to ensure that they're additive. That is, combining two stars that are close together makes things brighter rather than one occluding the other. So we use the blend mode source alpha 1 to get the additive blending with the transparency. We want to turn Z-test off. All stars should be drawn, so there's no need to check which are behind others. Indeed, if you don't do this, you'll get some artifacts as it doesn't blend them properly. Finally, for the tags, we just use the background queue. This makes sure that they're rendered first for things that are meant to be in the background, which fits perfectly for stars. So back in starfield.cs, we only have a couple of things to change. After getting the reference to the material, we can set the shader to be our new one. We use shader.find and pass in the name unlit star shader. As we added the scaling to the shader, we can remove the local scale and instead pass the underscore size to the shader with the setFloat command. That's it, but I'll just add one helper function. This is the onValidate method, which will be called whenever we update things in the inspector. Specifically, we care about when you change the size of the stars. We just iterate through all our star game objects, getting a reference to the material and setting the size variable in the shader. This isn't particularly efficient, but this is just to allow us to play with the settings in real time. So let's jump back into Unity and see this in action. Firstly, I don't know how well this will show up with the compression on YouTube, so let's bump the star size up. Now 100 is a little bit crazy, but you can certainly see the additive effect of nearby stars is working well. I'll leave it at 10 for the sake of this video, but in reality I think 5 looks great. Looking at the stats now, we've drastically reduced the triangles and vertices and the code is running great. Again, we can see Orion in front of us. There's the belt and the other 4 bright stars that form the constellation. Speaking of constellations, wouldn't it be great if you could highlight Orion like this? Now I'm sure you'll agree that looks pretty cool. So in the final part of this tutorial series, we'll implement the logic to toggle on and off a few of the constellations. I hope you found these tutorials useful so far. As ever, the full code is in GitHub, linked in the description below. See you next time.